Good morning to everyone. I'm Irene Sala from University of Milano Bicocca and I present to you Debt Hunter, a machine learning-based approach from detecting self-admitted technical debt. In this study, I collaborate with Antonella Tomasella and Francesca Arcelli Fontana. The presentation agenda follows these points. I will explain what self-admitted technical debt is, then I will provide an approach description and Debt Hunter tool description. I will present the research questions useful for analyzing Debt Hunter's performance. Then I will show the approach performance and in the end I draw the conclusions of the study. In this study we focus our attention on a particular type of technical debt, self-admitted technical debt. In literature, technical debt is described as a shortcut taken by developers to achieve short-term goals, like release quickly and on a budget. But what is self-admitted technical debt? Self-admitted technical debt is the debt intentionally introduced and documented in code comment or issue tracker. Generally, developers write comments to inform the rest of the team that the current implementation is not optimal or need future maintenance. Here are reported some practical examples, but in the above method, or to do enable can-proper tests. In literature, there are several self-admitted technical debt detection techniques. The pattern-based techniques manually find recurrent patterns in the comments that can lead to code smell, bad implementation, architectural smell, and other code issues that can be the source of debt in software implementation. The patterns are defined as a particular combination of words or symbols that are generally used when debt is expressed in the source code. Potdar and Shibab and Maldonado proposed pattern-based approaches. The automated approaches instead build machine learning-based classification models. They identify self-admitted technical debt or self-admitted technical debt types. Liu proposed an automated approach. The study goal is to create an automated natural language processing and machine learning approach for identifying different types of self-admitted technical debt in source code comments. We have identified 5 types of self-admitted technical debt: defect, design, documentation, test, and requirement debt. It is also proposed the Debt Hunter tool that exploits the presented approach. It could be used in a continuous evolution settings to monitor the development process or make developers aware of how and where self-admitted technical debt is introduced and help them manage and resolve the debt. Approach description. The approach takes in input code comment and make data cleaning, removing irrelevant elements for classification like punctuations, duplicated comments, and empty comments. 2 training data are created. The first contains comments labeled as self-admitted technical debt or non-self-admitted technical debt. The second instead contains only debt types comments. They are separately preprocessed with tokenization, stop word removal, stemming, and using TF-IDF algorithm. Then the classes are resampled using the undersampling or oversampling technique. The most informative features are extracted with InfoGain and using them, the classifiers are trained to classifying the comments. In the end, the models are tested with test sets. The training sets used present a class unbalance problem. To mitigate this problem are used resampling methods. Debt Hunter tool description. The approach proposed in this study is embedded into a practical tool, Debt Hunter. It allows developers to use the approach in an easy way. The 2 use cases of the tool are comments labeling and new model training with labeled data. The first use case takes in input source code comments or issue tracker, extract comments with parsing method, and classify the comments with depth counter or with the user's pre-trained model. In output, we have labeled comments into CSV file. The depth counter pre-trained model might not adequately generalize to any given system. It can be pre-trained with new data. In this sense, the second use case takes in input labeled comments, pre-process textual data, select the most informative features, and train classification model. In the output, we have trained models. Research questions. The 3 research questions of this study are shown below. Can depth counter outperform other self-admitted technical depth detection techniques in the literature? RQ1 analyze different automated classification techniques. Can feature selection improve the performance of self-admitted technical depth classification? RQ2 analyze a different number of features. Can data sampling improve the performance of self-admitted technical depth classification? RQ3 analyze different sampling methods. The baseline methods considered are binary, an automated classification between self-admitted technical depth and non-self-admitted technical depth that implements SMO. All labels, an automated classification that identifies self-admitted technical depth types over all comments and implements libsvm. Liu 2018. It replicates the automated self-admitted technical depth detector approach by Liu et al. It identifies self-admitted technical depth and implements NBM classifier. PB is a pattern-based self-admitted technical depth identification with Potard and Shibab's pattern list. Finally, MAT is a pattern-based self-admitted technical depth identification by Zhaoqiang, Guo et al. Authors. The first RQ compares raw data counter that implements SMO without using feature selection and any resample method with binary or labels, Liu 2018, PB and MAT. Raw data counter achieves the best performance and in terms of metrics, it outperforms all other baselines. Raw data counter is also statistically better than all other baselines. The second RQ analyzed the impact of feature selection of the 2 classification steps separately. The best configuration of the first classification step selects 750 features. The configuration with 5,000 features is also good, but the smallest feature set decreases the computational complexity. The second step obtains the best performance considering 3,000 features in the training set. This configuration achieves the best recall and F1 score over all other configurations. In the last RQ, we analyze the usefulness of the resampling methods. We compare spread subsample, SMOT, and the configuration without resampling method. For the first classification step, the configuration spread subsample 110 achieved the best performance with the highest precision and F1 score. Also non-resample achieve high performance, but considering the lower training set, we can decrease the computational complexity. In the second classification step for RQ3, the best performance are achieved by SMOT 50%, SMOT 100%. The SMOT configurations are statistically better than the spread subsamples configurations. To avoid the overfitting problem, we choose SMOT 50%. we can observe that the final configuration of the Tanter e-test with feature selection and resample method obtains the highest performance and F1 score, comparing the intermediate configuration, find answering RQ1, RQ2, and comparing all other baseline methods. Considering separately each depth type, we can see that Depth Hunter can outperform both raw Depth Hunter and all labels baseline. In conclusion, in this study we developed an automated approach for identifying self-admitted technical depth types. Also, the Depth Hunter tool is proposed. It exploits the automate approach and provides two use cases: comment extraction from code comments or issue tracked, and train a new classification model using labeled data. Answering the 3RQ, we found that Depth Hunter outperforms all baselines, and the best configuration is: first step, select 750 features and use a spread subsample 110. The second used 3000 features and smooth 50%. In future, we can use a semi-supervised model, add a new slang to clean, and implement deep learning model. That's all. Thanks for your attention.